So to help understand the problem, I listed out all the symbols given to us in the initial formula. So we're going to start with acceleration of t, and this is just our general acceleration function. The units are meters, just like squared. X hat and y hat just denotes which direction each function is referring to. Our variable is going to be time, which is denoted as t in seconds. Ti and tf are initial time and final time. Capital T is S constant time. That is unknown. So currently the two unknowns are final time and capital T. Alpha and beta are both known. And to help find the units, I did that to the left there, where we just set the acceleration function to its variable or to its unit. Then we solve for the units of alpha and beta. Next, we're going to have initial velocity, which is going to be 0 since we know the helicopter starts at rest. And then we're going to have initial position. And initial position can be anything. Since we're trying to find the change in velocity for this function. So what we actually start out doesn't matter. So we decided to choose 0, 0 since it would make the most sense with our graph. So it would just be the simplest choice. And assumptions that we had to start with were acceleration in the y hat is not necessarily g because there's not g because we know we're not on Earth, so it's not going to be the 9.81 or 10 value that we're used to. Helicopter, we're also going to assume that the helicopter is only moving the y hat and x hat direction. Since it doesn't mention a z hat direction, it makes sense to just ignore it. And then we're also going to assume that the surface of Mars is not flat, and we might not end up on the same y value that we started at. So like the helicopter might land higher or lower than it started at. And then we're going to assume any forces such as wind resistance are already factored into the acceleration or that they are negligible.
Right off the bat, we can see this is a vector value function of acceleration with respect to acceleration in the horizontal x component and acceleration in the y component of the vertical component. Straight off the bat, we can see that we have a bunch of scalar multiples being added to each of these functions. And what we can say essentially is that whatever value for either beta, big T, or alpha, they're only going to really scalar shift our graphs of acceleration with respect to y and respect to x. And in that sense, we don't really need to worry about them for right now. And actually, one of my compatriots will go into explaining why we don't have to worry about those for right now. All we really have to worry about is this t, or this little t value here, that's going to basically make the shape of our graph with respect to our horizontal acceleration and our vertical acceleration. So I've done that here, where I've broken down our acceleration vector value function into t of x and then t to the power 3 minus t to the power 5y. From these graphs, or from these functions rather, we can infer our acceleration in our x component, just worrying about this here. We have a linear trend with respect to time. So what that would generate in terms of our acceleration of our horizontal is a graph that looks something like this. So continuously increasing in acceleration with respect to time. Now looking at our y component here, it's a bit more complicated as you have a quintic function acting upon a cubic function, which seems like a very strange graph to graph, but I've done already is plug this in Desmos, and our acceleration with respect to y will look a little something like this, where we have sort of a rapid acceleration, a plateau, and then a rapid deceleration towards the ground, which makes sense in our y component because our helicopter will go up and then we'll want to go back down at some point. So from these two graphs, we can actually infer what the motion will look like in both the x and y direction. So in the x horizontal direction, if we make this our little helicopter guy, it's just going to continuously increase and increase and increase with respect to time, as we see here. Now our y component, or height component with respect to our little helicopter, is going to start from an acceleration of 0, slightly increase, increase, increase. We're going to have a plateau, so our acceleration is staying constant, and then our acceleration, positive acceleration, is going to slightly decrease, 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 until it gets to about 0, as we see here, and then it's going to rapidly decrease towards the surface of Mars. Now, we can combine these two phenomena together. So if we say this is our y-axis, or height, and this is our x-axis, we can start to infer, okay, so we're starting with a linear acceleration in the x component, and we're adding a bit of y component, slowly starting to go up. Our acceleration is going to be sort of dramatic in the y component, then we're going to hit that plateau, acceleration is going to be constant, and therefore our speed is going to be linear, and then slowly starting to come back down until we reach an acceleration of 0, and then a rapid decrease in the y component, but as still as x is increasing with respect to time.
Here I have 3 equations. This one I'm going to tackle first. It's from the problem itself. It's the t component is equivalent to the negative capital T being some kind of time constant. Because we know t is in seconds, and capital T is not multiplied by anything with units, it must be deduced that it also has the units of seconds. Up top, I have two equations that were found in the solution video. We have delta x, which is the change in position in the horizontal axis, delta y position, which is the change in vertical position over the course of the helicopter's flight. Because these are position, we can deduce that they must be in meters. These numbers here, 2, 105, 2, and 3, unitless scalars, they can be completely ignored for the unit section because they don't have units themselves. And because t here has a unit of seconds, it will be given the units seconds squared because it's in seconds. In these positions, we're trying to find this unknown constant. In the vertical position, it is alpha, and in the horizontal position, it is beta, seconds squared. Doing some quick division, it can be found that beta has the units meters per second squared, and alpha also has the units of meters per second squared. This unit is typically used with accelerations, so it can be deduced that alpha and beta are some kind of acceleration constants in the horizontal and vertical position respectively. Here I have a position function, or the position function from the solutions video, broken into the x hat, which is the horizontal position, and y hat, which is the vertical position. Within that, there are two components. There is the negative component denoted in red, and the positive component denoted in blue. As the positive component gets larger, it gets more positive. As the negative component gets larger, it gets more negative, and vice versa. First, I'm going to cover important scalar quantities, alpha and beta. Alpha and beta are important because they multiply every value of t by the same quantity, which is important because it doesn't change any important value of t, such as intersections of the t-axis or the t-value of parabolas or vertices. But what it does change is it does change the scale of the equation. By increasing beta or alpha, you scale the equation up, making all the slopes more dramatic, and therefore increasing the position at any point, which makes a lot of sense because, as discussed in the previous section, they have the units meters per second squared, which suggests that it's some kind of acceleration constant. By increasing alpha and beta, you would be increasing the speed at which the acceleration of the helicopter at any given point without changing the time in which it's in flight, which makes sense. You wouldn't change any important value of time, but you would change the position because it's moving at a faster speed in the time. Speaking of time, we're going to discuss capital T, which is the time component. It represents the halfway point of the flight. So if the helicopter flies for 10 seconds, capital T is 5 seconds. And the reason why this is so important is because it affects the positive and negative component of both the x hat and the y hat in similar ways. In the positive component of x hat, it multiplies. In the negative component, it divides. In the negative and positive component of y hat, it divides both sides. But in the positive component, it divides it by a smaller magnitude, only to the power of 3, versus in the negative component, it's to the power of 5. So by increasing capital T, you are making the negative components smaller than the positive components, because this would decrease at a slower rate by increasing capital T. And this makes sense because capital T represents the time in which it's at flight, and by increasing T, you are increasing the time of the flight. And by increasing the time of the flight, you are increasing the potential change in position, and therefore allowing the helicopter to cover more ground. So it makes sense that by increasing capital T, the position both horizontally and vertically gets more positive. Finally, we have lowercase t, which is the time component, which just represents the time of the helicopter in flight. As you can see here, in both negative components of both x hat and y hat, they are multiplied at greater magnitudes. In the y hat position, it's to the power of 7. In the x hat position, it's to the power of 3. And the reason that t is important is because it changes the shape of the line, the actual shape of it. And because the negative component is larger, we can deduce that it must be some kind of negative polynomial function. So for a parabola, it would be concave down, etc.
So we're going to start with total time, which I found by multiplying capital T that we got in the video times 2, because he said capital T is half of total time. If we take total time and set we're going to set D equal to 0, and we're going to find the limit as D approaches infinity. These are helpful because 0 and infinity weren't chosen arbitrarily. There are two extremes in this case, which is really helpful for finding out if our answer makes physical sense. So if D equals 0, total time is also going to equal 0, because if the helicopter didn't move physically or horizontally at all, it's also not going to move vertically at all. And if it's not moving, there's not going to be any time interval because it never left. So there's not going to be an initial time, there's not going to be a final time. Total time is just going to equal 0. Or we're going to find the limit as D approaches infinity. So then, and also the math for D equals 0 is right here. And then the limit as D approaches infinity, we're going to get total time equals infinity, which makes sense because if the helicopter is moving over an infinite amount of distance, it's going to take an infinite amount of time no matter what the acceleration is. And then we're going to test delta x equals d and delta y equals alpha over 35 beta times d. So if d equals 0, delta y is going to equal 0, which once again makes sense because if the horizontal distance is 0, that means the helicopter didn't move at all. If the helicopter didn't move at all, there's going to be no change in vertical space, which means delta y is going to equal 0. And we could find the limit as d approaches infinity for this one as well. However, it would just give us infinity, which isn't super helpful. And then delta x equals d, we already know this because it's given to us, but if we want to test it, delta x equals d at d equals 0 is just going to equal 0, which once again also makes sense because it is not going to be moving at all.
This problem is very similar to other problems that we've done in physics simply because it's a projectile motion equation. You're given information about the movement of an object, and you can manipulate that equation to find information about constants and other information about the movement, such as acceleration, velocity, or position. I will say that this problem was very similar to the homework 3, activity 1, and activity 3, simply because, again, it's projectile motion. However, I will say that this was much more difficult than other problems that we've done in class because the time components were to higher powers and were more frequent, so it was more difficult to calculate. And in addition, I will say that there were many more constants that we had to be aware of. And our group especially had a difficult time with the capital T constant and what it really meant and how it affected the equation.